there's this kind of transition stage. We have a lot of debate. There's also a lot of confusion. Where are we? What does the replication crisis mean? What are these paper mills? Are they affecting the hardcore science or not? What is the value of this whole thing? So I do want to take a moment to talk to you about this thing called replication crisis. And I want to start with this as a way to demonstrate some of the challenges that we're facing. Okay? So this is a paper that came out 2-3 years ago. It's actually not from psychology, but this is the longest running replication project that actually started back in 2012, 2013. And this is started with the Center of Open Science. And this is a relatively new center that started because of all kinds of case studies that I will come back to. It's very, very small. You don't need to understand everything that goes on here, and I'll guide you through this. But I'll just start by saying that this is from cancer biology. So let's say, for example, judgment decision making. If my stuff that I publish, somebody tries to repeat this and they fail, I have to say, as much as I would like to think that what I do is important, no big loss. Okay? Cancer biology. This is cancer treatment. So if cancer biology treatment does not replicate, if we don't know if something works or not works, people suffer, people die. There's a real outcome to this not being replicated. So in 2011, we started doing a lot of replications to try and understand, is cancer biology solid or not solid? What do we know about this? And we started from designing 193 experiments. What we did is we went to the article, we started reading the article and said, okay, we want to repeat exactly what it is that they did over there. But immediately we faced a problem. What kind of problems can we have from trying to repeat something from an academic article? How many of you have read an academic article? Very good. Paywall is the #1 challenge. First, we can't even read the article. Very good. So we don't have access to this. Actually, I have a lot of slides in there about paywalls, but we're not going to talk about this today. This is a corrupt system that we really need to tackle. Very good, paywalls. So basically, you, taxpayers, are paying a lot of money to me to pay for my salary and pay for my research. And then I take everything that I did and I submit this to a journal. And then somebody else from Vin University peer reviews my article for free. You pay their salary, right? And after we do all of this, what do? We give it for free to a for-profit publisher that puts it behind a paywall to charge you access to the money to the research that you funded, which is completely ridiculous. There's no reason for this to exist. So a lot of issues with publishing, we'll get to this. Let's say that we're very lucky and in Vin University we have access because our library is paid hundreds of millions of dollars to these for-profit publishers, and we can download this article. Or alternatively, we went to some Russian website and we downloaded it. So supposedly we have access to the article. We go to the method section. What happens then? What is the challenge? It's very, very short. Who knows what they did over there? Who ran the study? In what room? What time? Even if we have these details, somehow we know a little bit about the sample, maybe 50% male, 50% female, we don't really know. We want to follow the procedure. Actually, there are no details over there, right? A little bit easier with judgment decision making in psychology because we can maybe try and figure out, oh, they use this scale? Okay, I'll go back to the 1970s to find that scale and run this again. But this is not the same in cancer biology. Cancer biology, you need to know exactly what to mix with what, how to combine different things, what is the timing. So they start from 193, but when they start reading the articles, what happens? They only can conduct 87 of them. Why? Because this fails something that we call reproducibility. We don't have enough details in the article in order to know what happened. Now, what would happen if we write to the authors and ask them, excuse me, the article is not full, not comprehensive, I need more details. What do the authors usually say? No, usually no response, nobody answers. If they answer, what do they answer? A lot of different excuses for not having any access to the procedure. Even if we get the procedure, we want access to the data, we want access to the code, we don't have access to them. So they only started conducting 87 out of 193. Already here, you should feel discomfort. What do you mean? You pay for this. You pay for this research. You want to know that this is available, especially here in Vietnam. Let's say that this is conducted in some other country in the world. We also want cancer treatments, right? Why can't we access this information? So we need to talk about this jump from 193 to 87. But even further than that, even when they receive the details, they realize that details don't work. So actually, how many did they complete? 50. 50 out of 87 out of 193. Very, very troubling. This is not what I expected of cancer research. So when I think about science, everything is solid. I think about things that work. And we're not even talking about replication. We're talking about reproducibility, right? So we have a main challenge just to get things started. Now comes the big question, going back to the replication crisis. Okay, we conducted 50. How many worked? And this is where the big shock came. So after over a decade, hundreds of authors, people from around the world, invest millions in trying to replicate stuff that was previously done. It's a little bit small, so I'll just read this out to you. Succeeded on all three criteria. Out of 23 papers, how many succeeded? 2. Out of 50 experiments, how many succeeded? 2. Out of effects, 158, how many succeeded? 13. So the rate, if you look at the percentage, is what here? 11, 6%, 13%, 18%. This is a big disaster. Cancer biology. This is what happens out of the 50 that we were able to start conducting. These are the rates that you were expecting. This is not the rates that I was expecting. So you can see over here what's called the p-value, this elusive concept. I'm sure that if you take your faculty and you sit them together in a round table and you go one by one, what is the p-value? It will give you different answers. I've tried this at University of Hong Kong. People don't have a good way of defining p-value, and many of them get this wrong, even if they're statisticians or psychology professors. So here we have a p-value. Let's assume that the p-value is something that's important. We look over here, original findings, all of them lower than 0.05. If you look at the replications, all over the place, from lower than 0.05 all the way to 1. So you can see original effects and all the way from the replications up until 1. So to us, this is a disaster. This is unacceptable. If this is the way science is, then we're in serious trouble. We really need to clean up this mess. And if this is happening in cancer biology, I can see this happening in many other fields because people take cancer biology very, very seriously. If this is how we treat serious sciences, then we have a big problem with all the rest. Now, coming back to stuff in psychology, what are the costs? So we saw hundreds of authors, millions of dollars invested in this, and this is the ones that we check. We don't know how many people try this in their labs, their undergraduates, or in their PhDs, or just try to do the same thing again and again. We don't know how many of them were not successful. Here, we have an estimation about a finding in psychology that doesn't replicate. How much does it cost? This is an estimation by Sanjay. Sanjay had a very good podcast before, and he decided to quit academia and move to work in Meta. This is what he wrote in Twitter X. $1 billion spent chasing a flashy, unreplicable finding about something about the activation in the brain. What happens if you give a drug to somebody in psychiatry? How does this affect brain? So somebody published this, p-value lower than 0.05. And since then, people have been trying again and again to publish this. How much money have we wasted on this unreplicable finding? For this small psychology thing, 1 billion. This is the estimation. Actually, some estimations go far beyond that. What could we have done with $1 billion US? Lots of great things, right? So you can go back to cancer biology, you can go back to other things, but if you want the details of where this is, you've got the links over there to see the discussion. So this is just a small taste. I give a whole semester of examples about things like that. And then this is just a case study. I want to make this a little bit quicker because we only have 3 hours. And I want to summarize this by saying, so how big are these issues? And for me, these are very, very big. So this is the biggest thing that I want you to have, but these issues are very, very big and we need to tackle them. Now, some people might be saying, oh, this is just cancer biology. There's no problem in other fields. But I've been collecting headlines for more than 10 years now. And you can see that it's not just cancer research. It's also not just psychology. This is happening in medicine, this is happening in chemical research, this is happening in economics, this is even happening in computer science and mathematics. Talking about quantum computing, reproducibility crisis. We can't get things to work the way that they were published. So this is happening not just in psychology, not just cancer biology, but it's happening across the field. This is a science problem. Now, I don't know much about chemical and computer science, but I do know social psychology because this is my field. So I'm going to summarize for you the findings for social psychology. The biggest shock for me was 2015. It was 2015, something happened in social psychology that doesn't happen very often. In other fields, especially medicine and all of that, physics, they get a lot of publications in the top journal in science. And just so happens that the top journal in science is called what? Science. So we have journal Science, and we have journal Nature, and we have all these top reputable, we all want to publish there. If you publish there, it's a career for life. You're settled. All is good, right? So we social psychologists actually don't publish much in science. Happens very rarely, but happens. 2015, one came over here. And what they did was the replication crisis. 100 different effects. Many labs from around the world tried over 4 years to repeat classic findings in social psychology from our top journal. So we have 3 different journals. 2 of them are very, very well known in social psychology. And one is Psychological Science, very reputable journal in our field. And the second is Social Psychology. It's called the Journal of Personality in Social Psychology. We'll come back to this journal in a bit. So they try to take 100 findings from these 2 journals and repeat them. What did they find? Only about a third of them replicated, and in the things that replicated, the effect size, the manipulation impact was about half. So here you can see the science paper, and then we have many labs 1, many labs 2, many labs 3, and all of the rest together aggregated, summarized by the founder of the Center of Open Science, the same Center of Open Science that conducted the cancer biology. They are also the ones that did the replication for all of the findings in social psychology. What is the summary? I'll read this out to you. Across 6 large-scale replication projects, replication rate is 90 out of 190, 47%. And in the things that replicate, it's about impact of half. Effect size is about half. So at the beginning, the reactions were, of course, things in psychology don't replicate. We didn't really expect very much from psychology because psychology is not really a science. If it's a science, it's a weak science. It's the science of blah, blah, right? So compared to all the other hard sciences, this is not something that we expect would replicate. And then they said, how about we go to the best journals, we go to Science, we go to Nature, and we only take from these journals. We don't care about psychological science. And this is what they did here. We replicated 21 social science experiments in Science or Nature. What was the replication rate? 13. 13 out of 21. And once again, the impact, the effect size, was about half. Here, in many labs too, 28 findings, 60 plus samples, 7,000 participants, we studied, 186 authors. And just imagine how much money was invested in all this. All this just to show that we have a big problem. So this is my unofficial summary. I've been tracking this a long time. 2015, I was doing my postdoc in the US, and I was devastated by this. Because at the end, when we take all of this together, we have 30 to 50% success rate, and in the things that replicate, the effect size is about half. What does this mean? 2018, when I first started to teach you guys, undergraduates, advanced social psychology, judgment and decision making, they gave me a book. They said, please teach this book. This is the book of social psychology. And I started to go the book page by page, and then I realized half of the things over there, I already know don't replicate. And in the other half, I have a coin toss. Maybe it works, maybe it doesn't work. If it works, to what effect does it work? Strong effect. I'm very confused. I thought to myself, how am I supposed to teach this to undergraduates, or tell this to practitioners, or go on TED, or write books about this when I actually don't know what replicates? And everything is kind of like a coin toss. If it's 30%, it's even worse than a coin toss, right? We don't need science to be random. We need science to be credible and solid, right? So when I go around the world and I talk to people about these challenges, I get very common reactions from people telling me that I'm hallucinating. That actually there is no problem with science because look, there's electricity, the planes are flying outside, everything is working, we have apps, we have computers. What do you mean science is not working? How can this be? So I just want to tell people, I have already reactions to all the things that people say. So people say at the beginning, no, it's just psychology. I'm just showing you from cancer, biology, it's not just psychology, and I collect headlines from many other fields that have similar issues. So this is not a psychology problem. Some people say, this doesn't affect me. How can this not affect you? Everything in science is dependent on these issues. We need to know about them so that we can confront them. If you do science or consume science, and we all consume science all the time, then you need to know about this. Some people say, but I know that my research replicates. And my question, and you should ask this in your labs of your professor, is like, how do you know? How do you know that your research is solid? Have you given this to many labs around the world to replicate? If you published something 15 years ago and haven't touched it since, how do you know that it still works today? How do you know that it works in Vietnam? Right? If you ran this in Princeton during the 1980s on a sample of 20, how do you know that it holds for eternity all over the world? Right? So when we go and we look at these amazing TED Talks, they are so confident because they ran this little study in their own university, and then they say to the world, follow my advice. Right? My question is, typically, how do you know? What have you done in order to make sure that this is credible? Right? But people say there are hundreds of publications, so it must be true. So I'm actually going to demonstrate to you today that you can have hundreds of publications showing p-value lower than 0.05 on a single effect, and still for it not to be true. So we need to know how to make sense of all of that. And some people say, I personally found it again and again, and I'm going to show you once again that we are human, and we have weaknesses. And we study judgment decision-making So we know just how much bias there is in our minds, even when we conduct something like science. So science could be pure. Science could be objective. The main weakness about science is conducted by us scientists, and we're human. So we are the weak link in all of this. Okay? So now that we understand at least my view on things that could be very different from other people's view, I'm going to discuss some of the challenges. And I think it's important that we understand where this is coming from. So I'm going to discuss a series of problems that we need to acknowledge and understand about science and how to confront those. I'm going to show you how we do hiring. And this actually comes from a published paper that you can go and read. And this is very similar to, I think, how Vin University does hiring, how academia in general does hiring. So I want you to take a moment to think, let's say that you're the hiring committee, and you can choose the next professor in the Vin University department. And I want to give you a very simple dilemma, okay? So here we have two candidates, and both of them want to be professors at Vin University. They all have the same kind of PhD, they come from the same department, so they both got 2,000 participants, both of them, about 50% right about their hypothesis, both of them do similar designs, so let's say they both run ANOVAs, right? And they look at stuff that typically has an average effect size, okay? So they're similar in every way, but over the last 5 years, the main difference about them is that candidate A published 33 statistically significant papers, and candidate B published 21 statistically significant papers. Okay? So this is what you know about these candidates. And the question to you right now is you need to vote. Who do you want, candidate A or candidate B? Okay? Think about this for a second. Let's do a little bit of a vote. How many of you would go for candidate A? Raise your hand. Candidate A? Okay, why candidate A? Yeah, they publish more. What does this say about them? More credible? Yeah? Yeah, something like this? Yeah, why is this more credible? What does statistically significant mean? Why is it more credible? Very good. Let's keep going with this. As far as you can go. Okay, very good. It's very good to admit this. First of all, we don't know what it means. Second of all, we use this as a proxy for credibility. Right? Very good. Any other reasons to choose candidate A? Why else would we choose candidate A?
Produce more people.
Maybe more hardworking, right? They work so hard, right? And maybe they're better with the system, maybe they know how to get papers published, maybe it's an indication of how many they will publish in the future, right? Very good. We want to know how many of their findings actually replicate, right? How credible they are. Instead of using a proxy, we want to have an actual number of how many things replicate, right? It's a little bit costly because it means maybe if the replication is conducted, maybe more than the cost. Very good. Anything else you want to know about the candidates?
If we look at the average rate published every year, we look at it's 5.6 papers per year, right? But for that it's 4.2.
Okay. Yeah. What are you getting from this?
So if we look at the, if we look at the time they spend per each research, I think there is a bit of a diversion when it comes to the amount of time they can spend for each research. And again, you have to take into account their health and social circumstances. If you spend maybe only 3 months per research paper, people would have a doubt about the quality of that kind of research. But if you spend like 4+ months for a research paper, then it will be a better guarantee of quality.
Very good. So there are those who are claiming that maybe slow science is better science because we take our time to think about things, right? We invest more in the time that it takes to conduct the research. And maybe we're also better health, work-life balance. That could be, right? Yeah, we want work-life balance, very important. Very good. I have another question for you, very similar to the first one. Once again, we have candidate A and candidate B, and they're exactly the same about everything. Candidate A published 10, so they have the same resources and everything. During the last 5 years, candidate A published 10, high impact factor, all these science and nature. But no preprints, no open science, no pre-registration, no materials, data code sharing. Candidate B published in Diamond Open Access, lesser known, nobody knows about these things. No impact factors, but everything has preprints, so everything is shared openly. It's conducted with pre-registration. We'll talk about what is a pre-registration. And most importantly, everything, all the materials, the data are available. So take a moment to think, who would you prefer here? I can just tell you, there's no doubt in my mind, definitely for HKU, University of Hong Kong, and I think also for Vin University, typically when I go around, nobody has any doubts. Candidate A is by far the winner. Okay? Now, I want to tell you that I've also conducted these things on Twitter X, used to be very active over there. Now all of us moved to Blue Sky, but they don't have polls yet. So I conducted a lot of polls on Twitter. So I asked people, what do you prefer? Do you prefer the high impact factors, or do you prefer the open science stuff? And you can see that by far, people prefer the high impact factor stuff. I also added a bunch of other questions. So I said, let's say, for example, candidate A and candidate B have exactly the same number of publications. They have exactly the same resources, publish exactly the same number, but some of them come from Vietnam, some of them come from, let's say, in the UK. Some of them come from Vin University and HKU, some of them come from Oxford and Cambridge. Who would you prefer? I was shocked that everybody just said they wanted Cambridge and Oxford. And I was thinking, but why? They accomplished exactly the same thing. If anything, Cambridge and Oxford have a lot more resources and privilege and access. We, in Hong Kong and in Vietnam, we did a lot more with a lot less. So this is already showing you judgment decision-making. People have biases. They want the big names, Cambridge, Oxford, right? University of Hong Kong, where is that? Vin University, who heard of this? So no, we want what's familiar, we want the big names and the brands, right? But actually, people who were able to compete as much as the Cambridge and Oxford actually overcame a lot more challenges in order to do this. So I kept asking all of these things and kept getting the same kind of cognitive bias. So I wanted to tell you that across the board, with all the questions that I asked, it's always candidate A, candidate A, candidate. And I want to go back to the question of how do we know credibility from the little information that we have? So let me just tell you, and I think this is hidden, we don't see this at first, and this is a big problem. It took me a while to explain this to the University of Hong Kong Psychology Department. If they have exactly the same resources, it depends on how much they invested the same resources in order to get these papers. So actually, candidate A had less participants per condition because they had exactly the same designs. So candidate B actually invested 4 times more in the number of participants per condition. Okay? Why do we care about number of participants per condition? Because actually you wanted to know replicability rates. This is exactly what it gives you, because if you only have 25 per condition, it shows you that 15%, you can very easily calculate this, 15% is false positive, replicability rate is 25%. How about candidate B? Drops down to 6% of false positive, and the replication rate rises to 76%. So how they use the allocated resources matters a lot. People go for the thing that's visible. What's visible? 33 significant papers, right? Statistically significant papers. What people don't understand is what it took to get there. And people ignore that they have the same resource. So how do they distribute this resources? So I really like that you raised the amount of time invested. That's one factor that we can look at. But it's also, how did they allocate these? So there is an implication for how much you put per condition, how you use the resources available to you. And actually, in science, we need candidate B a lot more than candidate A. Because candidate A, at the beginning, can look like a superstar. But then, 10 years later, cancer biology comes, replication rate, and then we can't get any of this to work. And suddenly, candidate A is the one that wasted billions of dollars. Big problem. We don't know how to look at these things. And we need to discuss this as departments. Who is the candidate that we want around us? Okay? In terms of the high impact factor journals, there's a lot of things that we need to consider. This is a pyramid. It's very, very small, so I'll just let you know. It's by a person who will come back and talk about, called Chris Chambers. And Chris Chambers, we owe a lot to because he's trying to change science, and he built this pyramid. And in the bottom of the pyramid, we have something in red. And as we go up the pyramid, it becomes green. Green is where we want to be. This is closer as possible to credible science. The bottom, the red, is not solid. So he says over here, status quo research, the research that we're doing right now is not good enough, should not inform policy. We should not give this to practitioners of the media. How to change this to be a little bit better? We need data materials open. We need to make this available. Why is it important to have open materials, data, and code? Because this way we can reproduce, we can validate. We don't need to move from 193 to 50 conducted studies. We can have 193 conducted studies. So reproducibility is very, very important. What else? There's something called pre-registration. So pre-registration is fighting all kinds of biases. We'll come back and we'll talk about this. Then there's something called a registered report. And then there's something called a meta-analysis of registered reports. So the more we move up towards open science, towards sharing, towards validation, the more that we know that things are credible. So great that you've got 10 high impact factor journals published. So what if this doesn't replicate? So what if we don't know if this is solid or not? So could be that you publish the one in the bottom, published in a low impact journal. However, their research is a lot more solid. And I've been to a few lectures by Nobel Prize winners, and many times the lectures sound very, very similar. They had something new, destructive, they submitted it to Science Nature, reject. Moved down to things like PNAS, reject. Where did they end up publishing all of this stuff? The revolutionary stuff after that they got the Nobel Prize for? It's typically these dynamic open access. Because at that time, typically all these things go against what is usually published, and there's gatekeeping, and they say reject. So there is a lot of value beyond open science to these dynamic open access. What they care about is not whether you go with the mainstream, they care about whether you're credible. So very important that we have these dynamic open access as long as we do all the open science stuff. Okay? Now, in methods class, we usually talk about statistics, ANOVA, we talk about t-test and correlation, but we don't talk about what is considered to be a better type of evidence. So perhaps you've heard of all these different types of studies. Some of them are just like expert opinion. How do we know something? We go to an expert and we ask, does this work right? And then they give us an answer. We can do a little bit better. So for example, in the business school, usually they do case studies. So we try to analyze Tesla, Elon Musk, Microsoft. How did they become so successful? What's the problem with case studies? Yeah, how to generalize from this. It's very, very difficult. So if I follow exactly what Elon Musk did, or what Bill Gates did, will I become a billionaire? Will I build the next Tesla? What can I learn from this? Not much. Why? Because for every Elon Musk that succeeded, there are millions of people who did exactly what Elon Musk did and did not succeed. Survivorship bias. There's a lot of problems there. We don't see all the failures, right? If we take the same problem to vaccination, so let's say that I am a pharmaceutical company and I conducted 100 trials over my vaccine, right? Only 2 of the 100 worked. If I submit, I write all of them as different articles and I submit this to the journals, what happens? The 98 that didn't work, the journals say, it's not interesting because it didn't work, so we don't want to publish this, so reject. What do? You put this in the file drawer. What happens with the 2 that work? You say, oh my gosh, a vaccine works. We must publish this because this is revolutionary. This is going to change everything. So finally, the people who read this, who don't see the 100, they only see the 2 that are published, what do they end up thinking? Oh, the vaccination works. So the end result is not just a single case, not just the success published. We need to see everything, the good and the bad, because if you publish everything, then you realize it's 2 out of 100, not 2 out of 2. So very, very good. You need to really think, does this generalize? Does this really represent all of the sample? We go up a little bit, cohort studies, and then we have the best evidence that we can, randomized controlled trials. Very difficult in some fields to do this very, very well. You need also large samples in order to gain some. And finally, we have something called a meta-analysis. So we need to move up the pyramid in the level of evidence that we have. So meta-analysis of randomized controlled trial gives us causal evidence in support of some kind of treatment, vaccination. But we need both of these. We need to move up to meta-analysis and we need to move up into open science research. Now, let me tell you about the problem that I've been facing every day since I joined academia. Actually, I did not realize this when I was an undergraduate. I did not realize this when I was a master's. And even when I was doing my PhD, I didn't realize that this is the kind of world that I'm going to be facing. So on one side, there's me trying to do credible open science. So I'm trying to do systematic replication, and I'm trying to do things that are both novel and replicable. So here we have novelty and replications, innovation and maintenance, collaboration, all these things. But what does the University of Hong Kong emphasize? What are they looking for? They need to go up the rankings, and HKU is very good with rankings. It's considered one of the top universities in Asia. But what they care about are impact factors and rankings, the QS, right? Or the Shanghai ranking, right? And what they care about is novelty, groundbreaking, counterintuitive. So there's this difference pulling in different directions where I want to do credible science, but I'm being hired, promoted, and funded based on how I produce these findings. So I want to be the candidate A that gets a job. I don't want to be the candidate B that gets kicked out, right? So I have a lot of incentives to work towards what my university emphasizes. There was a very nice paper from 1975 by Stephen Blackford, and it's called, it's kind of like fancy English, but it's called On the Folly of Rewarding A While Hoping for B. You are rewarding one thing, but you're hoping for another. Back in the 1970s, he wrote this about something else. He wrote this about something that doesn't make sense. Up until today, we get hired for the research that we do. But actually, most of our job is to do what? We teach. We teach students. Nobody ever asked me to teach a class at the University of Hong Kong before I was hired. They just look at the number of publications I have. But actually, most of the value that I give to the university is in terms of teaching. I influence hundreds of students. If I'm a bad teacher, the university has a big problem. So folly is the mistake. The mistake of rewarding research while hoping for teaching. They hope for good teachers, but they reward only research. Same things happen with open science. You hope that you reward accuracy and credibility, but actually what you're promoting is prestige and novelty, right? Number of publications, no work-life balance, right? Produce as much as possible. Right? Then you hope that maybe it's accurate and credible. This is a big problem, so we need to address this. Now, you might think, okay, but researchers are not like that. Researchers don't do these things. Because we're noble, we're good people. We care about credibility, so we just assume that we don't respond to these kinds of incentives. Professors are too good for them. Right? We don't follow these things. And up until 2011, we really believed in this. But then in 2011, some things started to happen. Now, we have a group of practices in methods, in research methods, on how to run ANOVA, t-test, and correlation that we call questionable research practices. So we're going to talk a little bit about that. So you can see scientists say eating chocolate can help you lose weight, as they rule down cocoa, eating chocolate can help you lose weight. So next time you want to do something, just go and buy a lot of chocolate and eat as much as possible, and everything will be okay. What could go wrong? What could be wrong about this? How can it be? So good question. Luckily for us, it's a real study. But the person who did this study wrote a blog post explaining the study, and this is what they wrote. This guy here, John, I fooled millions into thinking chocolate helps weight loss. Here's how. I'll read this to you because it's a little bit small. Here is a dirty little science secret. If you measure a large number of things about a small number of people, you are almost guaranteed to get a statistically significant result. The credibility that we talked about before, right? Our study included 18 different measurements. So they didn't just measure weight. They measured cholesterol, sodium, blood protein levels, sleep quality, well-being for 15 people. And what happens when you have a very small sample? Have a lot of error, right? The larger the sample, smaller the error. So we have all kinds of ways to measure error, standard error, confidence intervals. You will learn a lot about these as you start to do some research. But what happens when you do 15 people is that it can go all over the place. Now, if you only did weight, then statistically, this should not happen a lot, that you find a statistically significant result. But if you have 18 different measures, because of the randomness of the universe, one of them will come up significant. Okay? Even if it doesn't, you can do all kinds of other interesting things. For example, you collect the data, you look at the data, but unfortunately, p-value is not lower than 0.05. P-value is 0.07. What do? You look at the data and you say, it doesn't make sense because I invested so much money in the study. I need to get something out of it. I need to publish in Science and Nature because this is how I get hired in Vin University. What can I do? One subject was dropped. Why? You look at this and you say, oh, I remember this participant was sick that day. Exclude, right? But in the paper, we don't write that we did this after we looked at the data. So when we take out this participant, with all of this 15 people and 18 different measures, that study design is a recipe for false positive, showing a positive statistically significant result that is not true. It is false. So it turns out there's ways to game the system in order to help you show support for something that does not exist. Nice of the science writer to have this kind of demonstration. A lot of people were, of course, very upset by this because they already started eating a lot of chocolate cream. They were going to the gym. So I'm just going to go and show you a parody. I hope that you'll be able to hear this, but actually it doesn't matter if you can hear this or not because it's in Spanish. How are you supposed to know what Spanish means? Hola is very, very good. It gets a little bit more complicated than that, but actually, what I want you to get away from this is not what he actually says, because what is this? I mean, this guy is a very famous Mexican guy, and he has something very, very unique in this scenario. And someone from the open science community said, this video is so great that I want to put the open science stuff on this, even if this is not what he said. So in order to understand this, you'll need to be able to look at the English. If it's too small here, you can look at the different screens. But I call this interview with a researcher about how to conduct research in order to get this into Science and Nature. Okay? Let's try and do this. All right.
Y me llama el cocinero. Recita, ¿qué? Ve por la paellera. Venga, que las 2 de la tarde ya están aquí. Y mira el bañador, en las chanclas. Todo despeinado porque no me dio tiempo nada de ponerme las chanclas y el bañador. Voy a la playa, había subido la marea. Jesús, había subido la marea incontrolable para ella. Y la encontré porque estaba la paellera agarrada metida entre las piedras de chipiones del faro. Y cuando entro en el restaurante me ve el cocinero con una paellera y a ver solamente paellera. ¡Asómate, mira dónde llega el agua! Llegaba el agua hasta el restaurante. Había subido la marea. Jesús, ¡ay, qué hacemos ahora! Con los 2 sacos de arroz. ¡Ay, llama para Sevilla! ¡Llama a Sevilla que traigo un poquito! Jesús, yo con el bañador y con la paella. El cocinero. No vea, a Sevilla. Y al último que cuando ya salió la bien de regla, estamos llorando los dos. Me cobró el tío la paella. Me cobró a 500 metros. Y ya no fui más. Me fui andando a cuello amarillo hasta hoy. Me mandó por la noche, había bajado más el agua y por la mañana había subido. Cualquiera estaba aumentando la paellera, a lo mejor está en el barco ese del petróleo.
En el Prestige.
En el Petrillense.
So I'm going to show you simulations. Actually, in my courses, I show 4 different simulations, but we don't have enough time for this. I'm going to show you one. And I'm going to demonstrate to you how to get paper out of nothing, out of random noise, just like the chocolate study, okay? Learn this together. I just need to be next to my computer, so forgive me for that. This is the main one, the first one that I'm going to open. It's called Let's Be Hack. It's an app that is written on R. So R is a coding language that we use for statistics. And what's nice about R is that it allows you to create a Shiny app. And a Shiny app allows you to simulate a lot of things for people who don't know how to code, okay? So it gives you this really nice interface. Actually, I'm going to make this a bit bigger. Yeah. And what you can see here that it's called p-hacker, training your p-hacking skills. So questionable research practices, we sometimes refer to as p-hacking, how to hack the p-value in order to become lower than 0.05. And we're going to simulate data here. And I'm going to create data that should not have any p-values lower than 0.05 because it's actually random noise. It has no effects in there. You can see over here that you can type in your favorite effect. So for example, here I will write chocolate eating compared to the control group. And then we're going to have the number of participants in the group, in each group. So about the same one as the chocolate study or candidate A, if you remember candidate A. True effect, coherence D. This is the kind of effect that you get from a t-test, right? 0. Should not have any effect in there. Everything that you see here is random noise, okay? And then we're going to add something. Number of DVs, I'm going to put this to 10. So I can't have 18 like the chocolate studies, but 10 is good enough for us over here, okay? And then I'm going to run the experiment, and all the p-values will start appearing over here. And all this is random noise, and it will already run the t-test for us, the ANOVAs for us, okay? So we're gonna run the simulation. Over here, we're gonna run this experiment. And you can already see something over here, it's a little bit small, but you can see there are 10 different DVs. And this is the summary of all the DVs. It's a little bit difficult to see, but this column here is already green. Not super green, a little bit green. Why? Because p-value is 0.085. This is getting close to a science publication, right? What can we do about this? So now we're thinking, oh, DV7 looks very, very promising. Maybe we can do something with it. So luckily, the simulation is already giving us the plot over here. You can see the plot, right? So you're looking at this chocolate eating versus the control group, and you're looking at this and say, oh, this looks very promising in the right direction, because this is weight loss. So chocolate eating really increases weight loss. But we see over here that something here doesn't make a lot of sense, but what I can do is I can take out this one here because I remember he was not feeling very well that day. If I go back to DV number 7, I have p-value lower than 0.05. Now I can publish. This is great. Good for me. Is it good for you? Random noise, true effect of 0, some real problem, right? So this is very obvious hacking. Now we consider this to be a big, big problem because it was not planned in advance. It was not pre-registered. So doing this after you look at the data is now considered to be questionable research practices at minimum, if not outright fraud. You should not be doing this. But actually, there are other ways to do this. So we don't need to be this extreme. We can do something else. So I'm going to bring back this participant because we want the full sample. And then we're going to go here, and there's a little tab here that says now p-hack. So I'm going to move to this one. And you can do all kinds of other things. So for example, you can add control variables. You can control for social status, you can control for age, for gender, for the interaction. Because you have a lot of covariates that you can add, every time that you add a covariate, it influences the p-values. They go up, they go down. You can start adding everything that you measured. Finally, you will get to p-value greater than 0.05 for DV number 7. But I'm not going to show you this because this is too trivial. I think a lot of people know that covariates influence the findings. We're going to do something different. It's called optional stopping. So here you see, add 5 participants, add 10 participants. And when I was doing my PhD, 2009 to 2014, I did not know that this is a problem. So sometimes questionable research practices don't come because people are deliberately trying to do something. They have an intuition that maybe they can get a result this way, but we didn't know the implication of this. Okay? So I'm going to show you something that I realized only after when all this certification stuff started to come up. And this is called the dance of the p-values. So p-values, I didn't realize, they go up and they go down. And if you look at them enough, at one point in time, something is going to come up and see. Okay? So what I want you to do is, as I add participants, I want you to look at what happens to the p-values. Okay, so start from DV number 7. Keep your eye on this. I'm going to add 10 participants. And then I want you to see what happens to all of these DV. So I add 10 participants. What happened? DV number 7 disappeared. So no longer close to 0.05. So much for my science and nature. Big problem. What can I do? I'm going to start adding more and more participants until something interesting happens. So keep your eye on the p-values, okay? I'm adding 10 more. Already we have 80 participants. I'm adding more. Okay, some of them become gray. I'm adding more, I'm adding more. Now we already have 140 participants. Look what happened to DV number 1. Suddenly the p-value gets a little bit closer to 0.08. All this is random noise, should not be p-value lower than 0.05. Okay, add 10 more. Now we're getting very close, 0.06. Adding 10 more. It's here, that's too bad. I almost got it, right? I'll keep adding. I'll add one more. Okay, what happens? Add 10 more. And suddenly you see DV number 9 is getting very close, p-value 0.08. I add 10 more. The only thing that I did is that I added 10 participants, I looked. I added 10 participants and I looked. This is called peaking. So I didn't say in advance I'm going to collect 240. I didn't do this. I just, every time I brought somebody in, I could have done this. Instead of adding 10 participants, I could just call each participant, come in, okay, what's the p-value? Okay, not enough, come in, not enough. So this is a real problem. Here's how we get p-value greater than 0.05 for at least 1 dB. Now you might say, 1 dB is not enough for a science paper. Can we get 2? You want to see if we can get 2? We can add more, so let's add more. Add more. 10 more. Now DV number 5 is starting to look good. Then we have DV number 7 and DV number 9, and DV number 5 is getting closer. So it's amazing. When you peak all the time, then it exponentially increases the chances of you finding p-value lower than 0.05. Now we know, it wasn't clear a decade ago, but now we know that we need to compensate for that. So actually, every time that we peak, every time that we look at the p-values, we actually have to divide the p-value by half. So if you peaked once, you need to change the p-value from 0.05 to meeting 0.025. Because the p-value, because you peaking increases the chances of you finding this. If you don't compensate, if you don't change the alpha, the p-value, then you increase the chances of you finding. If you run this enough times, you're going to find 2, 3, because the dance of the p-values, they go up and they go down. It has nothing to do with whether there's an effect or not. So we started from before saying statistically significant. We use this as a proxy for credibility. You can see over here, no effect whatsoever. There's a p-value going at 0.05. From the chocolate study, we saw you can get statistically significant findings for something that doesn't make any sense. Yeah? So I want to give you some tools on how to know whether literature is solid or not solid. In a bit, I will show you some case studies of things that we thought were super solid, but now we understand that they are not. How do we know this? We developed tools. These tools did not exist a decade ago. Now that we realize that our questionable research practices and people do this, we want to be able to see whether in a published literature, whether if we have a lot of articles saying that something exists, whether this is credible or not. And we can do this based on p-values, but not because they're statistically significant. Because over many, many studies, we have a certain pattern for p-value. So I'll show you what that looks like. This is another shiny app, and I strongly recommend to you, and I tell this to all my students, before you go and do a thesis, if you see an effect, go to the literature, take out all the effects, and put this in this p-checker in order to see whether this is credible or not. Okay, let's do it. So you can see this is the p-checker, the one for all p-value analyzer. What you can see over here is that actually this app knows how to read all the statistics that you can find in your article. So for example, ANOVA, F, or a t-test. So a t-test, all of degrees of freedom equals the statistics of, so for example, a t of 47 equals 2.1, okay? So what you do is you can extract all of these statistics from an article. 2 years ago, I would say there's an app called StatCheck that you can use. Actually, you can run a PDF through StatCheck in order to check the statistics and extract everything. But nowadays, ChatGPT, Gemini, Claude can do this automatically for you much, much easier and much, much nicer and will very well validate it. So you take all the articles from your literature, whatever you're interested in, you extract all of this and you put these here, okay? I'm going to show you an example of a literature that we call priming. We're going to come back to priming afterwards, but already now I'm going to tell you, we have serious issues with priming, social priming, okay? So somebody did this for us. They took all of the main articles from social priming and they put the results here. So I'm going to load this. So you can see here, elderly priming analysis by Daniel Lackens, who is a very famous guy in open science. And you can see that they coded everything. So they did, over here, they did all the ANOVAs and the p-values. They added all of this here on the left, okay? So somebody already did this for us. And now on the right, we have a lot of different tabs showing us different kinds of analysis to give us some indication of what is the credibility of this research. So here, for example, excess significance. Is there some kind of an excess significance here or not? We're not going to talk about this. First check that you can do is actually StatCheck. And StatCheck, what it does is it looks if the statistics are accurate. Turns out the person who wrote StatCheck, so Michelle, she is in Tilburg University in the Netherlands, her PhD thesis was to take all of the articles in the literature, take out the statistics, and just check is the p-value that is reported really the right p-value. And you can calculate this from the statistics and just see if it's correct or not correct. So this is what this tool does here. You can see reporting error, false, 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 so there's no error here. But if you scroll down to it, you'll see that some of them are flagged. And then you can see, is this a big problem or is this a small problem? But what I recommend to you, in your literature, just upload this here or upload this to StatCheck.io and then check whether there are some problems. Do this for mine, do this for your own lab, do this for everything that you build your research on, okay? So just know that StatCheck exists. Second thing that you can do, and this is amazing, you can already run a meta-analysis on this. So this automatically aggregates all of the studies for you in order to tell you what is the effect size across all of these studies. It even gives you a plot. So I'm going to show you this plot. What's interesting about this plot is that this plot gives you all of the findings under two triangles. One triangle is the triangle of null, no effect, 0. And one triangle is under the average effect size, in this case 0.5. Now, because of the way the statistics work, just take my word for it for now, generally the dots, these little circles over here, should disperse all around the triangle. They should be forming a triangle because of the randomness of the universe. However, you can see here something very strange is happening. The dots are on the right triangle, but the dots don't appear here on the left triangle. What is the difference? Why is this one empty, even though there's supposed to be some dots here? This is what we call a publication bias. Why is this a publication bias? Because everything that was not p-value lower than 0.05 was just not accepted for publication or not submitted for publication. So actually, there's a lot of different studies that are missing here, should be here, but are not here. So sometimes by conducting a meta-analysis and plotting it like this, you already see with your naked eye, you can see there's a publication bias. We didn't know this a decade ago. We didn't have these tools. Now we have statistical tests for this. So we can run these statistical tests. So you can see here there's Egger's test. So for example, here you can see that there's a bias. You can have Pete and Feast. There's a bias, there's a bias. So generally, we have a lot of statistical tests that are telling us that there's a problem in this literature. There's publication bias. What a bigger, actually, the next, there's one slide that I can show you. Right? This one shows the distribution of p-values in our literature. Generally, for healthy literature, most of the p-values need to be lower than 0.001. Okay? Then you will still have 0.01 and 0.02 and 0.03, but they should be decreasing. There should be less and less of those. Most of them need to be lower than 0.001, but then you will have a little bit of those. P curve, what it does is it looks whether the curve of the p-values follows this pattern or not. Here, this analysis actually shows that here it follows the pattern. So you can see most of the findings are lower than 0.01, then a little bit lower 0.02, a little bit lower 0.03, a little bit lower 0.04. But what happens at 0.05? Suddenly there's this huge jump that should not be there. Why is this huge jump? People are pushing their p-values to be lower than 0.05. So we can do meta-science in order to look at the distribution of p-values in order to see whether they make sense. So you can take all of the elderly primate literature, plot them like this, and see if they follow the expected pattern. If not, then the p-curve analysis is going to show us that this is a problem. I just want to go back to questionable research practices. And the question that you might have, and we had this in 2011, question is, are people really doing this? Are researchers really doing this? How to know? How do we know if people are doing this or not? And ask them. So in 2012, we actually did the first survey. So here you can see the results of the survey published over there. Are really people doing this? And we asked them, how many people are failing to report all dependent measures? Just like the chocolate study. How many of you are doing this? 78%. 78%. How many of you are collecting more data after seeing whether the results were significant? Peaking, optional stopping? 72%. How many people are failing to report all the conditions? 42%. So I showed you a parity, but actually the parity is very close to reality because we had a stat in 2012 that people are doing these questionable research practices. The most horrifying thing here is this one, falsifying data. How many people are doing this? So 9%. What you can see here is that we ask people both whether they self-admit to doing this, and then we ask them, do you think people around you are doing this? Have you seen people do this? And when we ask people whether they saw people doing this, you can see it arrives at 100%. 100% of people are doing this. This is not good, right? Maybe this was a fluke. This also needs replications, right? We need to make sure that this is solid. Maybe there's a problem where maybe the US is a problem, right? And the thing is that we kept doing this again and again. Here we're talking about psychology students, asking psychology students, are you doing the hacking? Are you not submitting null results? Are you harking? Are you doing optional stopping? You can just see you got all the way to 60%. And this is self-admission. This is not even, you can imagine that if people are self-admitting to do this, the capture rates are even higher than this. Finally, this is the last one that I saw from 2020 in the Netherlands, which is considered to be the most open science country in the world right now. Fraud. I'm just talking about fraud. 4.3 and 4.2 people report to having faked their data. That's not good. How do we know that this is a big problem? Because Daniel Lakens, the same guy who summarized the elderly finding for us, started to aggregate. So all these are studies that we've done, 2012, 17, 2020, 28. So he just plotted all of those. So how many people are doing something called harking? Hypothesizing after the results are known is harking. It means first I put the results and I say, oh, I know, I had this hypothesis all along. I'll pretend as if I predicted this. How many people are doing this? Up to 60%. How many people are excluding data? Just like we excluded the person who was sick that day? 60%, 40%. How many people are doing all this? You can see the rates, right? Not just one study, again, these things. We even have things that go up to 70%. Selectively reporting performed analyses, selectively reporting what worked. This is very, very troubling because it means Researchers, we would like to think that they're good people, that they don't respond to incentives. But of course they respond to incentives. Have lives, they need to get a salary, they need to support their families. When we motivate them, when we promote them, when we hire them, when we fund them, based on how many statistically significant papers come out, this is what happens. And this is just one aspect of a lot of different problems that we have. This is just questionable research practices. Combine this with other things we discussed, publication lags, or other things I'm going to show you, and we have a real problem. This is, I'm just going to say, from a month and a half ago. This is a case study. We're not going to get into in some details, but there's a very big fraud case in our field, in journal decision making, by a very high-profile researcher in Harvard. I'm supposed to say alleged fraud, but there's no doubt that the fraud happened. The question is, who did the fraud? She claims her RA or somebody trained her. But actually, many papers that came out from a person called Francesca Gino, we now know have fraud in them. The only question is, who did the fraud? Because of this fraud, all of her co-authors, a lot of them, she has hundreds of co-authors because she's very prolific, created a whole initiative called Many Co-Authors, where they tried to go and find out whether what she did with them is fraud or not fraud. Okay? This is the background story, but this is not about Francesca Gino. To my great surprise, somebody that worked with Francesca Gino published this on Twitter X. I'm going to read this out to you because this is really shocking. Came up a paper that they wrote together, and they asked to retract this. They said, this is not solid. We want this wiped out of the literature. Why is this retracted? Everybody thought it's because of Francesca Gino, because of this fraud. But no, she admitted on Twitter X the following. What did she say? I want to correct the record on two immediate false narratives emerging. First, I've seen no evidence Gino was involved in any of the studies beyond the pilot. So it's incorrect to blame Gino for the primary issues in this paper. So it's not about Francesca Gino. Why did you retract this paper? Second, there are issues in every study. I was the student investigator in charge of running studies 3 and 4 10 years ago. The key results in studies 3 and 4 were very statistically significant due to research practices now identified as p-hacking. What did she do as a student? Big shot professor from Berkeley, dropping daylight unclear exclusion rules. What does she say about this? I am ashamed of helping publish this paper and how long it took me to identify its issues. I am not the same scientist I was 10 years ago. So many people applaud her. It takes guts to be very brave to admit, I did this before, now I know better, I want to clean it. But if a big shot professor from Berkeley admits this, nothing to do with the fraud with Francesca Gino, then you can imagine how many people are doing this. We're getting to rates that are very, very high. Even the big shots, the ones that are candidate A, the ones that publish all these papers, are the ones that we should, asking to revisit things. Now I'll describe to you what started this whole thing. How do we know that there's a problem? Where did this all start from? So up until 2011, we were pretty ignorant about things. We didn't realize what was going to happen. But then, because of BEM in 2011, we in social psychology realized that there's a problem. What happened in this study? This is a study in one of our best journals. Remember, I told you we have two big journals, Psychological Science and Journal of Personality in Social Psychology. We want to get published in this. This is an A+ in social psychology. We have Daryl Bem, Cornell University, Ivy League, no doubt. He's very well known. He's actually one of the co-authors who wrote Introduction to Social Psychology, very well-known person in the field. And he published 9 experiments. 8 out of the 9 had statistically significant results for what? That people can feel the future. Very, very strange. I remember when this came out, we were very puzzled by this. What do you mean you can feel the future? So let me tell you what he did. So typically in a psychology lab, what do? You bring people into the lab, you show them some stuff, and then you see a response to it. So in our labs at the University of Hong Kong, we measure sweat, heartbeat, we do EEG, so we want to see brain activation, right? And typically, if you want to see the strongest effects, we show very strong stimuli. What is the strongest stimuli? How can we get the strongest reaction? What is the best stimuli that we have? How to get people to respond? Sorry? Threaten them, yeah, it's horror, surprise. You know these memes where you think you're seeing something and then suddenly something screams at you? Immediately, it's racist, right? So horror is one very good thing to get people to react. What is another? Pornographic imagery. You show them porn, people activate, their brain activates all the time. So there of them use erotic stimuli and horror. But instead of first showing the stimuli and then measuring the response, what did he do? First, he measured the response, and then he showed the stimuli. And he showed that people respond to something that they will see in the future. So basically, a social psychologist, very well known, has shown us something that physicists have been trying to understand for a very long time and have shown to be impossible. Time flows in a certain way. This is called psi. For us to show support for psi is impossible. It's an impossible result. So we thought, okay, there's a problem here. How come this is published? Because the editor and the reviewers didn't find any problems. One doubt is maybe this is fraud. They fabricated this. So they asked Dale Ben, can you please share your materials? Actually, he was very forthcoming. He shared everything with us. We looked at the data. We couldn't find anything wrong with it. We used the best methods that we had in 2011, and he was able to show 8 out of 9 statistically significant results. Now, many years later, after he admitted in a podcast to doing this, we know that what did he do? Optional stopping. Coming participant P. Coming participant P. Optional stopping. Started with them. Back then, we didn't understand what he was doing. How was he able to do this? And we realized if he's able to publish something that is impossible, then we have a serious problem with our methods. We just don't understand the implications of how we run statistics, right? So it's not about how you run your SPSS, t-test, or ANOVA. It's about whether you run the SPSS, t-test, ANOVA every time that you bring in a participant. So research methods are not just how you put stuff in SPSS, but also about the process of how you use SPSS. Very important. Now, we know that this is impossible, but this is already published, so we have a big problem. How do we correct this? What should we do? Should run replication. So we ran replications. Stuart Michi, this guy over here, now he's a very famous guy. I'll show you in a second what he does. Then decided, I want to try and replicate this. So he ran 3 unsuccessful attempts saying, I want to do this again, independent replication, not BIM running this. And I'm using best practices, open science, sharing everything. I cannot get this to replicate. So good enough, right? Submit this to the same journal. The journal should retract the other and publish this instead. What did JPSP say? What did this journal say? The reaction was reject. We are not the journal of failed replication on BIM. So what is your role? Why do you exist? What is your function? Why does this still exist out there? Why does it still get citations? So the only place where he was able to publish this is PLOS1. 10 years ago was the only place where he was able to publish a finding that is null, that doesn't have p-value lower than 0.05. So he's the first one who published this, PLOS1. Now it's a much more famous journal. Back then, nobody knew about this. After they published this, people are like, come on, JPSB, what are you doing? You have to publish something that shows that this is wrong. So another group of researchers submitted again. Now they have the same journal, JPSB, correcting the past failures to replicate site. And this is only after all of the movement together, open science element. It's not right that you only publish the original. Which one gets more citations? This one gets a lot more citations. How many of these are getting citations? Not nearly as many. And then we have more and more replications. All of them are failed because, of course, it's an impossible result. What does Ben say about this if you ask Ben? Ben is very, very good at finding all the flaws in the scientific method to show again and again that there is side. And every time we figure out something new in how he's doing these things, with a meta-analysis and other things as well. This is Stuart Nunn, published a book called Science Fictions. Strongly recommend this book. Terrific book, came out during the pandemic, and it really shows the entire journey of what he went with them. But he went much further than this. And he was a very successful researcher, very prolific, but he quit academia. He said, this is not the way I want to do research. What does he want to do? What is he now? He's a podcaster. He tries to help people understand how to evaluate scientific evidence. So the name of the podcast is Studies Show. So whenever you hear chocolate helps with weight loss, go to Studies Show and see whether this holds or not. So he and another person discussed studies to see whether it's credible evidence or not. So Stuart Ritchie does holy work in trying to help audiences understand how to look at statistical evidence. Daryl then didn't just stop at this, but he also gave a lot of good advice for students like you. So he wrote some books, writing the empirical journal article. And back when I was a PhD student, this was the advice that we read. Plan your article. Which article should you write? There are 2 possible articles you can write. A, the article you plan to write when you design your study, or B, the article that makes the most sense now that you've seen the results. They are very the same, and the correct answer is B. Correct answer is definitely not B. You should follow your plan. You do not do this, This is hypothesizing after the results are known. This is playing with the data. This is questionable research practices. So now we know that he was doing all these kinds of things because this is the advice that he gave. Any questions about this case study? This is the thing that changed everything for us. 2011. Because of them, we started doing replications. Because of the replications, the science paper came out in 2015. Because of social psychology, cancer biology, because of cancer biology. So this all started in 2011, seeing the future then. So social priming, we also discussed a little bit in the p-hacker, p-value, p-checker thing, that social priming has an issue. This is a paper from 1979, cited by thousands. So we have thousands of articles done on social priming, showing support for priming. What is this priming? Social priming is activating a certain mindset. Activating a mindset means that if you unscribe some sentences or if you show certain words, then it will get you to behave in a different way. So for example, John March in 1996, perhaps you heard about this, did something called elderly priming. So if you unscramble sentences about things that are related to being old, and if you measure how people walk from the room to the elevator, they walk slower. Social priming, thousands of citations. Okay? So you can see here they prime hostility. Now we try to replicate this. And you can see here that this is a big effort. I know a lot of these people because these are like all the open science people that I hang out with. Over here you can see that this is conducted by Randy McCarthy. Bob Wire, who is one of the original authors. So the first one was done in 1979. This one is done in 2018. So many, many years later, right? And Bob Wire was actually part of this. And they conducted a mass replication. And you can see just how many people are involved here. All these people. And finally, what they found is these results suggest that the currently used methods do not produce a priming effect that is practically and routinely detectable. Couldn't find any support for priming. Something that has more than 2,000 citations involving the original author. Okay. Big problem. Now, what should we do about the original article? Should we keep it there? Should we teach this to our students? Should we change everything? Should we take away the books? Should we take away the TED Talks? What should we do? What is the reaction of the people after they saw this replication? Did they change their opinion about priming? The answer is no. The people who do priming reacted and said, all these replicators did this wrong. Actually, the problem is that they're not priming experts. You need to be a priming expert in order to get this right. So you just being an undergraduate student at Vin University or a professor at University of Hong Kong is not good enough. You need to know how to do priming. If you would involve us, we did, but it didn't work out. But if you involve us, then we would know how to get priming to work. So what did we do in the open science community? We ran another application. Before I show you that other application, I just want to tell you that Randy identified issues in priming that have nothing to do with whether this replicates or not. So over here you can see the Twitter X, that some meta-analysis, so when we want to aggregate all of the results together, we put this together here, and you can see Cohen's D of 0.39, Cohen's D of 0.08, and Cohen's D of 5.65. How many of you know what is a Cohen's D? Heard about Cohen's D? No? So Cohen's D is the effect size, the measure of impact for a t-test. Okay? So I would say, generally, a weak effect is 0.2. An average effect in social psychology is something like 0.35. Strong effect is something like 0.5, 0.6. What is this, 5.65? This is an impossible effect. There is no way in the world that this is an effect. How to get you to understand that how big this effect is? So somebody used Shaquille O'Neal. He was a big NBA player back in my days, in the 1990s. NBA player 2.3 something, 250. So a Cohen's D of 5.65 is the difference between Shaquille O'Neal and the average female. This is very, very noticeable. So for something like unscrambled sentences and how fast people walk is impossible. So already we should have known a long time ago that this paper reports an impossible finding. So all these 2,000 citations, somebody should have found this. But nobody found this until Randy came here, even though there was a meta-analysis about this. Because we talk about the meta-analysis, I'll also point out these 5. What is the problem with these 5? There's a guy here called Staple. And he published a lot of priming results. What is the problem with Stapel? Another thing that happened in 2011 is that Diederik Stapel, who is the Dean of Social Sciences and Psychology in Tilburg University in the Netherlands, admitted to fabricating everything that he has done since the PhD. Over 60 papers retracted. A lot of people are hurt by this. Who publishes priming papers? Fraud or impossible effects. This is what's included in this meta-analysis. So we should have known. And when we go to Bob Wire and we say, hey, you know, this is an impossible effect, what does Bob Wire say? You're right, this is possibly a mistake. I didn't realize that this was a mistake. Why did it take so long for them to recognize this is a mistake? Did we really need to waste the time of all these people? Not just this, but in addition, this figure is very problematic because it shows four-way interaction for 80 participants, showing this kind of pattern. This is too clean, this is impossible, even the figure doesn't make sense. The results from 80 participants should be all over the place, very, very noisy. For something to come out like this should not be possible. Very, very unlikely. So Randy and a bunch of other people say, I find this why did it take us since 1979 until Randy in 2018? But because people told Randy, you need to know priming in order to do replications. What did Randy do? Poor Randy. Randy ran the whole thing again. So you can see over here, another group with 11 authors. All these people invested time again. They did 2 replication studies, each lab, one by themselves, and one they invited priming people to say, can you please help us? What did they find? Once again, over here, despite our best efforts to produce favorable conditions for the effect to emerge, we did not detect a hostile priming effect. You know how many people are involved here? How many millions were wasted on this? Twice. On something that we already knew from a long time ago, that this is impossible and this is impossible. Why do we need to do all of this? This does not make a lot of sense. Now, there's lots of issues here. We can go over all of the issues here, but there's a reason why I want you to focus on this case study. And this is because of somebody who's very close to my heart, unfortunately passed away last year, who I build all of my work on. And this is something very fundamental in our field of judgment decision-making, a person called Daniel Kahneman. Right? So priming literature, lots of case studies, we failed to replicate this again and again, failed, and a lot of problems for this. By the way, before I go on to Daniel Kahneman, I just want to say John Barge and the priming people, did they stop doing priming literature? No, they still publish these things. So here you can see a book from John Barge, 2018. Just before you know it, the unconscious reasons why we do what we do. And this is like a bestseller, New York Times, a lot of publicity, more TED Talks, more things. Here's a talk in Google that he gives, just to show you how unreasonable this is. What is he claiming here? I'll just read this out to you. No one has ever turned a conservative into a liberal. So I don't know if you're aware of what's happening in the US, but the Republicans and the Democrats are not talking. A lot of things happen. Donald Trump is now in power. Generally, very difficult to get the Democrats and Republicans to talk to each other. But he's saying nobody ever tried to convert a Republican into a Democrat. But if we have them feel physically safe, we have them imagine that they were given a superpower by a genie. So you go to a Republican and you say to him, because now you have a superpower, so you should feel safe. This makes them become liberal. So the people who are going to feel invulnerable to harm, the conservatives move much closer to the liberal attitudes as a result of feeling physically safe with them. So none of this makes, if you know anything about political views in the US, very, very difficult to change anybody's opinion. There's just saying something like this in an official talk in 2018, after all these failures to replicate, to say that you can tell people that they activate their mindset by telling them that genie gave them a superpower and they become liberals makes no sense. If you look at the p-values of these papers that come out, they're very, very low, very close to 0.05. So almost indicative, very, very likely for this to, if you put this under a p-curve and you look at all these things, these are very, very unlikely. Pushing these p-values to be 0.05. Unfortunately, I know some of these people. I work with them, even published with them, and I know that they're trying to do good research. So I don't know what leads to this, but I'm hoping that at least some of this will disappear over time. But John Barge is still very, very active, still publishes, has a lot of criticism of replications. Yeah. The thing that I want to show you, I'm going to skip this. So I run with all the undergraduate thesis students at University of Hong Kong, I run replication. So everybody who wants to work with me, instead of them having to do something novel and exciting, I just tell them, let's start with a replication. And we did a replication of a classic finding where we show that people don't understand statistics very well. And this is based on this paper. Belief in the law of small numbers. Who wrote this? Hanoi University and Daniel Kahneman. Why are these people important? Important because they are, or Daniel Kahneman, is the only psychologist to ever win the Nobel Prize. It's a big, big honor. Why don't we have more psychologists? Because there is no Nobel Prize for psychology. There's only a Nobel Prize for economics. But as these two psychologists did their research, they informed economics and created a whole field of behavioral economics, which is basically economics with psychology. Okay? Not many people know this, but the first paper that they ever published is this one, cited by 5,000 people.
Sorry.
And what they did is basically go to statistician conferences and give them studies just like the priming studies and ask them, how likely is this to replicate? What do you think? And they show again and again that even statisticians and even scholars, professors make mistakes when they look at studies just like priming with a very, very few participants, p-value just below 0.05. They consider them to be solid and credible just because the statistic is significant. So they are the ones that warn the world about this. Be very, very careful. Do not trust studies with a small sample size. Do not trust these studies p-value just below 0.05. So here's an example. They ask people in statistician conferences, suppose that you have an experiment with 20 subjects and you got p-value lower than 0.05. If you run this again on 10 subjects, will this replicate or not replicate? And they show that people are generally very, very optimistic about this. So Daniel Kahneman warned the world about this in the 1970s. The problem is that after he received the Nobel Prize in 2002, he wrote a bestseller. Perhaps you've heard about this. It's in every bookshop. Anything that has a psychology section has Daniel Kahneman, Thinking Fast and Slow. Chapter 4 or 5 has the marvels of priming, where he congratulates social priming, and this is the conclusion. The idea we should focus on, however, is that this belief, not believing in priming, is not an option. The results are not made up, nor are they statistical flukes. We have no choice but to accept that the major conclusions of these studies are true. Not only are they true, you must accept that they are true about you. So this came out in 2011. What happened in 2011? Two things, bam. Second thing, Dietrich-Stapel, fraud, right? The beginning of social psychology. So Daniel Kahneman, his book just came out. Suddenly this thing, he's getting very, very agitated and very worried. So what does he do? 2012, he gets really worried. He writes an email, and the email became public, so now we know about this. This is what he writes. From Daniel Kahneman, a proposal to deal with the questions about priming effects. As you all know, of course, questions have been raised about the robustness of priming results. Your field is now the poster child for doubts about the integrity of psychological research. People now have a question mark to the field. All I personally have at stake is that I recently wrote a book that emphasizes the priming. Count me as a general believer. He still, in 2012, believes priming literature. He still hopes that his chapter in Thinking Fast and Slow is solid. And you can see in Nature, all these things coming out. Oh my gosh, the Nobel Prize winner, Daniel Kahneman, Thinking Fast and Slow, has a book about priming, and he's calling on the priming literature to do more replication. After we started doing all of these priming literature replications, Paul Randy, right, twice. We've done all of this again and again. We have over 10 mass replications in many labs around the world. Priming just doesn't hold up. So he writes in 2017, see here, all this thing here is a blog. So by then, Daniel Kahneman is over 80 years old. He finds this random open science blog and goes and writes a comment. And this comment is really heartbreaking for me. Because this is what he writes. What the blog gets absolutely right is that I place too much faith in underpowered studies. It's pointed out in the blog and earlier by Andrew Gelman. There is special irony in my mistake because the first paper that Hanoi University and I published was about the belief in the law of small numbers, which allowed researchers to trust the result of underpowered studies and unreasonably small samples. Devastating. He warned the world about this, and then he fell into the same trap. Our article was published in 1971, but I failed to internalize its message. So what I want you to take away from this is that knowing about a bias or knowing about a problem doesn't mean that you're vaccinated against it. So if Daniel Kahneman fell into this trap, we can all fall into this trap. So we need to check ourselves again and again. And he writes again and again, and he comes back to this, and he really, up until his death, he's like, oh my gosh, I really got this wrong. I really got this wrong. So Well, I was wrong, at least in that case, the studies of behavioral programming that I had cited in the chapters are largely discredited. There were essentially no takers for my suggestion that primary research should do replication. So just to tell you, special anecdote, when I saw all these things come out, my question to Daniel Kahneman, I never got to meet him in person, but I really wanted to ask him, so you called the primary literature to check their work. Did you check your? Who is going to check your work? How do we know that your work is replicable? So I asked everybody. Nobody wanted to do a replication study. So who ended up doing replication studies? I did, with my students. So we conducted over 150 replication studies of Daniel Kahneman, of judgment decision making, of behavioral economics. We did this. And actually, I'm quite glad to say, for the most part, almost everything that came out from Daniel Kahneman, even 50 years later, still holds. We found some context, not every time, not in every place, not in every context, but generally seems to be a lot solid than the 30 to 50%. Our replication rate is something between 60 to 65, and even in the things that don't replicate very well, we have some idea of what we can do to improve. So we were the ones that took up this challenge. This is why I want you to get an idea of, even Daniel Kahneman fell into this trap, but he also had a biased blind spot where he called other people, why did you not replicate? But he still didn't do this himself. So all of us are biased, even the best intentions, even the best scientists, all of us are biased. There's just no way around it because we're human, because we're flawed. Just going to talk about this specific study. It's a great video. I strongly recommend that you watch it. I'll summarize this for you because I think it's a remarkable case study that you should know about. It's a viral YouTube video. Do you know this guy? Who is this guy? Veritasium. 3 million followers on YouTube. He is one of the most popular science communicators, influencers out there. So here, he showed something remarkable. He showed this. And this is a machine, a car, that is able to go faster. It doesn't have any engine, but it's able to go faster than the wind that's pushing it. So it's conducted in a sort of way, in a physics way, that he claims, showed a video, is able to go faster. What is the problem? Comes this professor from UCLA, physics and astronomy, big shot professor, very high credible university, goes to the YouTuber and says, you're absolutely wrong about this. This makes absolutely no sense. I'm a physics professor. What you just showed is impossible. Go and check yourself. So the YouTuber offered a bet. How about we bet about this? Are you willing to put $10,000 and we get the best science communicators, these guys, I don't know if you're familiar with them, very famous names in science, to be the judges on who is correct or not correct. Each side presents their evidence, and then they decide who is correct and who is not correct. Whoever loses needs to pay $10,000. Actually, I really like it, because I think we should do this more in science. If people do a TED Talk, or people do books, then they should put money on it. I'm going to make this very, very short. What I like about Veritasium is he really wants to get to the truth, because if I'm wrong, I want to know. Like the whole point of this channel is to get to the truth. And the professor came up with a lot of explanations about bias. So these things can be done unconsciously. I'm pretty sure, 100% sure, that the guy in the video doesn't do it on purpose. He said, you found the results a little bit like them did. You didn't. You just don't know how to use physics, and you don't know how to use statistics. Right? Very interesting debate. And at the beginning, when this was happening, I really wanted to, support the YouTube influencer, but a UCLA professor had been teaching physics for a very long time. What was the result? Who won? Yeah. So professor was wrong, the YouTuber was right. The physics professor from UCLA had to pay and paid $10,000 to the YouTuber. And actually, it's very easy to show that this works. Now, they have a 3D printer template that anybody can print for $3 in order to run this. So you got another YouTuber who just demonstrate this. So actually, the UCLA famous professor could have done at any point in time, just try to replicate this for $5. Did not need to pay $10,000 on this. This is ridiculous. A little bit like with Daniel Kahneman, where we think we're so right about something, it just makes absolute sense that this is the way to go. But even UCLA professors for physics have been teaching physics for a very long time. You need to learn from this. A lot of lessons, just mind-blowing stuff. My takeaway is that at any point in time, the professor could have checked this, why not replicate this, hubris, bias against replications, bias blind spot, and finally confirmation bias. Okay? So these are the case studies that I wanted to present to you to show that even us professors, even your professor, could be biased. It's really okay for you to ask questions. Your questions are great. I love the questions that my students ask me because you have not been brainwashed. I have. I grew up in an atmosphere that was wrong. I love it when my students come to me and say, but how is this possible? Can you explain to me? And somebody was like, oh, you're right. This absolutely makes no sense. So what I like about undergraduate students like you, first year, second year, is that you're still naive. You're not as biased as we are because you didn't grow up in the system. It's good for you to ask questions. If something doesn't make sense, please raise this. Please check us. On my website, I have a pledge. And the pledge is, check me, replicate me. I'm calling you. If you want to make some good money, please help me find mistakes. I will pay you. If you find a minor error, I will pay you $5. If you find a major error, I will pay you $50 because just like Veritasium on the YouTube channel, if I'm wrong, I want to know. Not 50 years from now when I publish my Nobel Prize winning book. I want to know this now so that I don't make these kind of mistakes. So this is why we need to work as a community. And you might be thinking, oh, but we are just students, we can't do this. So actually, every semester, my students check the previous semester students in order to see if there are mistakes, and they find a lot of mistakes, and I need to pay them a lot of money. So I actually give them the option, do you want the money or do you want to donate it? If they want to donate it, then I match it, and I double the money, and then we give it to charities. And almost all of the students want to donate. So in this case, for example, I lost or won, depends how you look at this, $250. But they found the mistakes before we submitted this to the journal. So that is great. So grateful for the students. This is how science should proceed. And even undergraduate students can find mistakes. So when you have questions, don't push this aside because somebody's going to even get paid for this. So I really like this, and I hope that your lab will have this. Right? I love this. In this lab, mistakes are expected, corrected. This is how we should do science. We should always revisit, always reassess, always check things in order to make sure that our science is credible. We should reward these things. We should invite people to check us. If somebody replicates our work, we should say thank you. What can we do to help? Not say, the dog ate my homework, I don't know this for a long time ago, but let's try and make this work. Oh, I also want to tell you that my students also found indications for all kinds of problems that led to other retraction. So here is a blog called Retraction Watch. A team of students led by me, a psychologist at the University of Hong Kong, found an error and that led to an expression of concern. So because the students checked things in my courses, then this was removed from the journal. And the person who did the mistake said, yeah, this is the way that science should progress. And I say students and early career researchers are the key to the science reform movement. You are the ones that I have all the hope for. I'm lost, my generation perhaps lost, it's going to take us another decade. But by the time that you will be there in the system, either in industry or in science, you will have enough tools and enough knowledge about this in order to help us change the system. So this is my general perspective. Some people say, but you're wrong. There's no science crisis. There's no replication crisis. There are no problems. All of these things, you're wrong. And I say, okay, that's fine. I see this a little bit like the climate change kind of thing. So some people say, we want green jobs and livable cities and clean air and clean water and healthy children. And somebody comes up and says, but what if this is all a big hoax? You would create a better world for nothing. Like, yeah, let's just create a better world. We all want these things. Who cares? Climate change, you say it doesn't happen. Just work together with us to achieve all these things. I say the same thing about with science. We want to prevent be happy, we want to increase transparency, we want to do education, open access, so we will have paywalls. What if this is all a big hoax to create a better science for nothing? Let's just create a better science. So right now, I have a lot of support that I didn't have 3 years ago. Until 3 years ago, I went around the world and I talked about this challenges and you told me, are you crazy? There's nothing happening. But luckily, since 2022, UNESCO agrees with the open science movement. And now UNESCO is calling for open science. So you need to join UNESCO in order to understand that this is something that's happening. Not just UNESCO, 2023 is the year of open science for NASA. Have you heard about this in Vietnam? We have not heard about this in Hong Kong. Nobody talks about this thing. Sorry?
Didn't they teach this in their electrical study?
I don't know. Maybe. Yeah, I hope so. If somebody's talking about it, this is terrific. Yeah. So it's just unbelievable that all these things are happening. And we started to have all kinds of solutions. The first solution is share everything. I know sometimes you need to anonymize, sometimes you need to hold some stuff back. We have solutions for this, but first share everything, materials, the data, and the code. Make it very, very clear so that everybody can reproduce what it is that you're doing. Everybody can check, everybody can see if there are errors in there. You don't need to wait 50 years. We need to pay people to check our work, incentivize credibility. We need more candidate B instead of candidate A. Because we care about the way that people conduct their research, not just the results and the outcomes, right? We need to support the diamond community, the community journals, not just the science and the nature and this obsession with novel findings. So open everything, validate everything as early as possible, welcome and incentivize a community and embrace and share mistakes. Mistakes are okay, as long as you find them, as long as you communicate them, as long as you correct them. So we need more of this pyramid, and we need more of these things from first make it possible, then make it easy, then make it helpful, then make it rewarding, then make it required. Last thing I want to share with you is what I think is the biggest revolution in science. I really hope that if you ever get to a point where you submit an article, I really hope that you'll submit it this way. I do all of the thesis students that do thesis with me submit to a journal as something called a registered report. The registered report is revolutionary because what it does is that it prevents all of the need for questionable research practice. How does it work? You develop the idea, you write a plan called a pre-registration plan, come up with the best plan that you can, and then you submit that to the journal. No data collected, just the plan. So then everybody together discusses this plan. Sometimes we get really good feedback from the reviewers saying, you didn't do this correctly, you should correct this. And we're like, okay, we can still correct this because we didn't collect the data. So we, the reviewers and the editor, come up with the best plan. And the great thing is, it doesn't matter what the results are. When we all agree on the plan, we get something called in-principle acceptance. And that means that here, after the stage 1 peer review, once we all agree, I already know that this is going to get published. Doesn't matter if p-value is lower than 0.05 or higher than 0.05. Doesn't matter what the contribution is. Doesn't matter anything. We all agree on this plan. Once I get the in-principle acceptance, only there I try to collect the data. What happens in stage 2? After I collect the data and I analyze this, I submit this, and I need to show the reviewers that I followed the plan, that I excluded what I said I didn't exclude, I didn't add anything, I didn't change anything, everything is reported. So in stage 2, we just make sure that it adheres to the stage 1, or if you have things to add, no problem, you can add as much as you want. You just need to be very, very clear what you followed and what you deviated. And everything that you deviated is exploratory. You need to repeat this again before you can say anything about it. So why is this important? Because suddenly there is no publication bias. It doesn't matter if p-value is lower than 4.05. It doesn't matter about anything about the outcome. What it means is that we all agreed on the same process together, working to make sure that we have the best plan. So we've done more than I've done with my undergraduate thesis students, more than 30 of these, and all of them were able to get in principle acceptance and get this published as a thesis. So something for you to consider. If you ever do a thesis, you can talk to your advisor about doing this. Chris Chambers, again, he's the one who invented this. So we need to open as much as possible the method, the data, our publication, the peer review, educational resources, everything made open as much as possible is better for everybody. I do all of these things with my students. We have a big team from around the world. If you want to know more about this, you can look us up. It's called the core team. If you want to join at some point, you feel like you want to contribute to this in some way, want to make some money, you want to just do the science, you want them to reach out to me. These are all the people that are involved, more than 390 people in my courses, all of the thesis students, everybody, and we've done a lot. So we followed up on Tversky and Kahneman and the judgment decision making, and we've done publications of over 150, which goes to show you can also do this. If I can do this with my undergraduate students, you can also do this. So you can choose what it is that's interesting for you and can repeat this. If you don't have something that's interesting for you, you can reach out to me. I'll give you some ideas. And a long list of things that need to be replicated are waiting for you. In addition, if you don't know how to use Jamovi, if you don't know how to use R, if you don't know how to calculate effect stack, if you don't know how to do a power analysis, if you don't know how to run replication, no problem. We have a collaborative guide for you. The way that we work is that we set everything up on Google Docs. So actually, you can get immediate feedback. If you see something that is missing, you can write a question and I will fix it. If you find something that is missing and you contribute this, you become a co-author. Most of my co-authors on most of these things are students, my students, undergraduates, teaching assistants. So what's nice about open collaborative resources is that they're updated all the time. We find mistakes and we update them. And everybody who contributes, doesn't matter if they're, everybody is becoming a co-author. As long as you just say what it is that you contributed, you're a co-author. And we have a lot of these resources. How to use spot checks, how to run this data collection. Just go use this. As an example, effect size, how to calculate currently. If you don't know, we have a great guide for this. It's amazing to me that we don't have a good book about how to calculate effect sizes. That we needed at the University in Hong Kong to start this. We were two students that are now PhD students. And then suddenly a lot of people from all over the world joined us. tonight's a collaborative thing. If you want, you can contribute as well. Everything that I mentioned, everything in my open science research, all of the resources that I talked about, all of the applications, everything is on my website. You can go on the website or scan this QR code, and you're very welcome to reach out to me. I see again and again that students are very scared of professors, writing to professors. Please don't be. I respond to every email. Even if I am busy, I will connect you at least to somebody else who I know from our team that can help you. I really want to make sure that you are on the right path. So if you have questions, something is unclear, if you want to know something more about open science, about anything that you heard of today, then please reach out to me, and I'll be happy to help you in the open science journey. You can follow me on YouTube. There's also a mailing list about all of our activities. This and other videos about open science in general to educate you more about the tools that are out there, and all the semester that I do with my undergraduate students about how to do better science. So hopefully this was helpful and useful for you. Happy to answer some questions. Stay here a little bit longer or reach out to me. Thank you.